Hi everyone, thanks for joining us today. My name is Don Smith at Texas Instruments. I will give a technical introduction to our Sub-1 GHz offering. This is a Level 1 presentation made for engineers with limited RF experience. The course is a mix of slides and hands-on videos demonstrating the development tools for the Performance Line family. We have split the training into 2 sessions. You are now watching Step 1. I will focus on 3 topics today. The first one is about radio range and coexistence. The next topic is how to achieve low power consumption by taking advantage of on-chip features especially designed to optimize battery lifetime and minimize MCU interaction. Lastly, I will present some of our development tools that will greatly reduce the evaluation and development times. Sub-1 GHz is the best technology for robust, long-range wireless communication. When creating an RF design, you need to decide what frequency band to use. As shown on this map, different regions have different regulations for industrial, scientific, and medical bands. These ISM bands are license-free, and TI provides solutions for all. Commonly used sub-1 GHz bands are around 900 MHz, Europe 868 MHz, US 915 MHz, Japan 920 MHz. All can be served by the same hardware printed circuit board. 433 MHz is also popular and can be used worldwide. Please remember that all RF-enabled end products must pass mandatory regional certification programs. Range is an important parameter in most wireless applications, and there are several factors that may impact the range. Antenna performance, transmitter output power, and receiver sensitivity are important for range. Other factors are coexistence and environmental conditions. Coexistence is the receiver's ability to perform well in hostile RF surroundings. Environmental factors include obstacles like walls, trees, etc., that will absorb part of the RF energy. The RF frequency also plays an important part in range. According to physical laws, lower frequencies give longer range, but both local RF regulations and antenna considerations limit the choice of frequency. In an ideal case, using the free space propagation equation, every 6 dB will decrease the range by a factor of 2. For example, improving the sensitivity by 6 dB will, in theory, increase the range by a factor of 2. Using antennas with 3 dB loss in both receive and transmit will reduce the range by a factor of 2. Sensitivity is defined as the signal power level required for a particular quality of received information. For digital radios, quality is measured by the bit error rate. The CC1120 has an impressive -129 dBm sensitivity at low data rates. The sensitivity limit is set at 1% bit error rate. The transmitted signal has a certain signal bandwidth defined by the modulation format and data rate. A higher data rate will typically give a wider transmitted signal bandwidth. On the receiver side, there is an RX filter that needs a bandwidth wide enough to fit the transmitted signal bandwidth and also to allow for crystal inaccuracies on both the receive and transmit sides. In the figure to the right, the RX filter is shown in red and is wider than the transmitted signal bandwidth. Sensitivity depends on the receiver noise floor. The minimum equivalent input noise for a receiver at room temperature is -174 dBm over Hertz. This thermal noise is independent of frequency, and taking the RX filter bandwidth into account, the noise floor is increased above -174 dBm by a factor of 10 log times bandwidth. The table at the bottom shows how the noise floor scales with the RX filter bandwidth. Note that the effects of the radio's internal noise, typically termed noise figure, is not included in the expression for noise floor above. Since transmitted signal bandwidth increases with data rate, there is a trade-off between data rate and sensitivity. Higher output power gives longer range, but maximum output power is limited by regional regulations. With the CC1190, TI has a range extender with a power amplifier that can transmit up to 500 milliwatts, which is the same as plus 27 dBm. This is the maximum allowed output power in many regions. Theoretical range is only possible for line of sight. Several factors such as obstructions, multipath fading, reflections, etc. will limit range. Lower RF frequency typically gives better range and penetration for the same sensitivity, output power, and antenna performance. Antennas are one of the most challenging aspects of an RF design. TI has a lot of offerings to make antenna design easier. The antenna kit and the corresponding application note give a great overview and measurements for many antennas. This includes multiple printed circuit board antennas, chip antennas, and helical antennas. The kit includes a total of 13 low-cost antennas in different sizes and form factors, in addition to 3 calibration boards. TI has a well-equipped RF lab, an antenna chamber, and can, for selected customers, offer to optimize the antenna solution. This involves the following 2 main tasks: impedance matching, so that as much power as possible from the RF transceiver is transferred into the antenna. Secondly, measuring the total radiated power in an anechoic chamber. This is a measure of the efficiency of the antenna. It is also possible to measure the antenna directivity, meaning how much power is radiated into different directions. There are several factors that influence range. 2 key factors are sensitivity and output power. Shown on this slide is a simple communication system with 1 TX transmitter and 1 RX receiver. To increase the range, you can increase the out power. Please note that the maximum output power is limited by regional RF regulations. Another way to improve the range is to increase the sensitivity. The sensitivity is influenced by many factors, but the 2 most important are data rate and receiver sensitivity. Typically, higher data rate gives shorter range, so it is important to find a data rate that fits the range and throughput requirements. The receiver sensitivity is the ability to decode an incoming RF signal. Given the same data rate, a good receiver is able to decode a weaker signal and hence give better range. I will give you an example. Around 50 kilobits per second will typically give full house coverage and a good balance between throughput and range for an alarm and security system. The example above is not a realistic field scenario. In real life, you will have interference. Interference can severely limit the communication range of your system. To successfully operate in a hostile RF environment, you need good coexisting properties. This translates to first-pass installation success. The coexisting properties of a device is defined by the selectivity and blocking performance. It is important to understand that better selectivity and blocking translates directly to better sensitivity and range in the presence of interference. This will be explained in detail on our next slide. Let's look at what coexistence means in an everyday environment using a smart meter network as an example. To the left, you see a system based on the TI sub-1 GHz performance line. To the right, you see a system based on a competitor device. The green dots represent data collectors. The yellow dots represent smart meters. Let's look at what happens if an interferer device enters the environment. In this example, let's assume a wireless headset. The wireless headset interferes with the range of the data collector, making it impossible to communicate with the far-out nodes. Since the data collector range is reduced, you will need more data collectors to have the same coverage area. Also, this is temporary interference. You will get higher packet loss and will need more retransmissions. Let's look at what happens in the same example using the system based on the TI sub-1 GHz performance line. The wireless headset enters the environment, but the range is not affected. The data collector maintains the range, meaning you can have less data collectors, longer range, and fewer retransmissions. Most wireless applications are battery powered, and to minimize the current consumption, the radio should be in sleep for as long as possible. Fast wake-up times are therefore crucial when designing an ultra-low power wireless application. TI's performance line radios have both fast startup from sleep to idle, which is typically 400 microseconds for the CC112X and 300 microseconds for the CC120X, and from idle to active mode 166 microseconds, and are therefore highly suitable for low power applications. In addition to fast startup time, another factor which is just as important is the time spent in active mode. The current consumption in active mode is typically much larger than the current drawn when in sleep or idle, so the time in active mode should be therefore as short as possible. When transmitting data, the time spent in transmit mode is determined merely by the packet length and data rate. The real challenge is to minimize the current consumption in receive mode, and TI's performance line radios have several built-in features designed especially with this in mind. While in receive mode, the radio will continuously measure the signal level, and if the level is above a pre-programmed threshold, a carrier sense signal is asserted. The time it takes from entering receive mode until the radio can determine if the signal is above or below threshold is called the carrier sense response time. If the signal is below threshold at this time, receive mode can be automatically terminated and the radio can go back to sleep without the intervention of the host MCU. TI's performance line radios are designed to minimize the carrier sense response time and hence the time spent in receive. This results in a very low average current consumption while listening for incoming data. A receiver needs to be able to know when a data packet starts. The data payload is preceded by a preamble followed by a unique known sequence called sync word. A traditional receiver often uses a bit-based sync word detector. The demodulator is generating a bit stream, and sync search is then done on a hard decision data stream. This kind of implementation requires a long preamble to achieve bit synchronization. Sync detection will be slow, and the sync word needs to be of a certain length to avoid triggering on noise. For a 16-bit sync word, there is 1 in 65,000 possibility of detecting a sync word in noise, meaning you will trigger on noise within a few seconds after enabling receive. If you trigger on a false sync word, you will spend unnecessary time in receive processing a false packet. The receive current consumption will increase, and you might lose the real packet being transmitted. The CC112X and the CC120X implement sync search using the novel wave match capture logic. The demodulator uses the sync word itself to do bit synchronization and to find the frequency offset, and it requires only 4 bits preamble for settling of the AGC. Sync detection will be very fast, and the likelihood of false sync detection is greatly reduced. Imagine if you input noise into the wave match detector, then the likelihood of a correct wave appearing in noise is extremely low. In a typical RF system, the packet consists of preamble, sync, and payload. A traditional receiver requires at least a 2-byte preamble for AGC settling. If the receiver uses a traditional bit-based sync detector, it will, in many cases, need to receive all or most of the preamble to be able to correctly detect the sync word. To ensure that enough preamble bytes are received, it will need to stay continuously in receive mode. CC112X and CC120X only need half a byte of preamble for AGC settling to be able to detect the sync word. This means that it can stay in sleep for most of the preamble and then wake up automatically to look for a sync word. The time spent in sleep is determined by the preamble length, and for a system using a 4-byte preamble, this means that the receiver can sleep for a period of 3.5 bytes and still be able to wake up and detect the sync word. If it wakes up and there is no signal on the air, it will return to sleep after a time and receive equal to the carrier sense response time discussed on the previous slide. It is an advantage to have hardware support for packet-oriented radio protocols built into the radio. Packet handling features, That's automatic insertion of preamble and sync words, CRC insertion and check, interrupt when packet sent received, etc., puts less burden on the MCU. Putting the MCU in low power mode until interrupt receive will reduce current consumption. In transmit mode, the packet handler could add the following elements to the packet stored in the transmit first in, first out: a programmable number of preamble bytes, a synchronization word, compute and add a CRC checksum over the data field. In receive mode, the packet handling support could deconstruct the data packet, preamble detection, sync word detection, address check, compute and check CRC. CRC is a checksum used to detect bit errors in the received message to be able to discard packets without valid data. Can disable everything and use as pass-through receiver. If the receive signal qualifiers are integrated in the radio, false error check can be done without MCU intervention. Put MCU into low power mode and wait for an interrupt that a valid packet has been received to minimize current consumption. Transceivers from TI have digital output pins, which generates an interrupt to the MCU if a packet has been received with OK CRC. This slide shows the basic concept of our tools, offering the radio product itself is normally provided in the kits as evaluation modules. Small boards with the complete reference design for the radio, including all the required components required for a fully functional RF design. These boards are the same as we used during the characterization of the chip, so they ensure data sheet performance of the kit. The evaluation modules can be connected to an evaluation board, a development and test platform for the radio. The platform can be used for software development and for hardware prototyping. The development board also provides the backbone for communication with the device from the PC. With the evaluation board and an evaluation module, tools like SmartRF Studio are used for radio performance testing, and IAR Embedded Workbench used for software development and can be used for testing and development purposes. SmartRF Studio 7 is a PC application that can be used in combination with several development kits for Texas Instruments CC-XXXX and CC430 RFICs. It runs on Windows XP, Windows Vista, and Windows 7, both 32 and 64-bit, and uses USB or parallel port for legacy boards to communicate with the evaluation board, which has an evaluation module with the RF chip mounted. A radio on a custom board can also be tested with SmartRF Studio by wiring it to an evaluation board or a CC debugger. SmartRF Studio 7 helps designers of radio systems to easily evaluate the RFIC at an early stage in the design process. The program provides an easy-to-operate PC interface to all of the chip's radio configuration registers and is very helpful for functional testing and for finding the appropriate radio settings. SmartRF Studio 7 can also be used without any hardware, but then only to generate, edit, and export radio register values. The main feature of SmartRF Studio 7 is the control panel for direct access to the RFIC's chip registers and radio-related features. It gives an overview of the many device-specific features and provides full read and write access to the chip's radio registers. The SmartRF Studio has two main operating modes. In Easy mode, the user can easily get started by using predefined register values and radio configurations. In Expert mode, the user can fine-tune all settings and is given more flexibility when configuring how the device should operate. All of the device configuration and register settings are stored in XML files, making it possible to add custom configuration settings and to parse and reuse the files by external tools. The new script extension is particularly useful for customers who want to automate some of the test functions found in SmartRF Studio. SmartRF Studio 7 is a major update from SmartRF Studio 6.xx and earlier. The tool has been redesigned from the ground up, focusing on flexibility and ease of use. The most apparent change is the new look and feel, aiming at making more information available and presenting it in an intuitive and easily understandable way. SmartRF Packet Sniffer is a tool that can be used for capturing and parsing of packets going over the air. The GUI quickly gives you an idea of what's being sent over the air. It can be a valuable tool for debugging and analyzing an RF protocol. The capture device is typically one of the nodes from the development kit, be it a USB dongle or an evaluation board, such as a SmartRF evaluation board with a radio evaluation module. Supported protocols are Bluetooth Low Energy, Zigbee RF4CE, Zigbee 2007 Pro, Simplicity I, Generic Protocol, Raw Data. The Sniffer's product page at ti.com/packetsniffer provides an overview of what capture devices are supported and what the capture devices can do. TI provides schematics and Gerber files for all products. Use the exact same values and placement of decoupling capacitors, balun, matching, and filter components. This reduces the likelihood of degraded performance in terms of output power, sensitivity, spurious emission, etc., and ensures faster time to market. TI can assist with a design review to avoid unnecessary board spins. The customer then needs to provide schematics and Gerber files. Before you set up an RF link, you need to test, receive, and transmit performance separately. To test the hardware with known good software, connect the SmartRF evaluation board to the radio on the prototype board and disable the MCU. With this setup, SmartRF Studio can be used to perform hardware testing, and no software bugs will affect the result. To test the software with known good hardware, the control lines from the MCU should be connected to an evaluation module. This can be done by plugging in the EM in SmartRF evaluation board and use one of the test connectors to connect the SPI and GPIO signals to the MCU running the software. See the development kit user manual for information about what connectors to use. For functional testing of the customer receiver hardware and software in a wireless link setup, you can use SmartRF Studio plus EB plus EM as the transmitter. This ensures a fully functional transmitter and will narrow down any potential problem areas and help debugging. Similarly, for functional testing the customer transmitter hardware and software in a wireless link setup, you can use SmartRF Studio plus EB plus EM as the receiver. This ensures a fully functional receiver. The sub-1 GHz market today is dominated by proprietary and legacy systems. Due to the differences in regional regulations, standardization on sub-1 GHz has been slow. Our RF devices offer full flexibility on all RF parameters to enable support for all types of legacy systems, from simple garage door openers to high-performance long-range metering applications. We have basic software examples that can be used as a starting point, including EasyLink to set up simple communications between RF nodes and a packet error rate tester to easily evaluate range. The Simplicity I software stack is a star network that is offered in source code and can be used as is, or as a starting point for development by a customer. Simplicity I is available and free for all TI LPRF devices. For Europe, Wireless M-Bus is a popular communication stack for metering, and KNX is a home automation stack. 6LoWPAN is a new RF technology defining IP version 6 packets on a low-power RF network. It is typically referred to as enabling mesh communications for both sub-1 GHz and 2.4 GHz. We offer 6LoWPAN solutions in collaboration with third parties. In this presentation, we have discussed how the performance line from TI will ensure long RF range by offering excellent sensitivity and output power as well as coexistence capabilities. This ensures a robust solution that will be able to handle a future we see a lot more RF products being used. New features like wave match and sniff mode makes it possible to greatly reduce the power consumption without compromising RF performance. The on-chip packet handling is also contributing to lower system power consumption and is in addition making it easier to design an RF solution. TI offers a lot of tools that come in handy for debugging and development. shortening your time to develop your products. This was our first part of the technical introduction to Sub-1 GHz. If you want to learn more, I suggest you continue to watch Step 2 with a hands-on video of SmartRF Studio and our packet sniffer. You'll find it on our TI training portal. We have a lot of information to support you going forward, and we constantly load new support materials. Please note the pages listed here. And don't forget that the TI E2E online community is the best place to go for support. Here you can search through thousands of questions and answers related to your RF design, as well as posting any new questions you would have. Thank you for your attention. Please do not hesitate to contact us at any time.